We're live. We're good to go.
Cool. Thanks for being here, everybody. Yeah, we're going to talk about vegan today. So it's a package for community analysis in R. It was designed for community analysis, although it's sort of a good way to implement a lot of different multivariate techniques in R. And so I'll be talking about it sort of more generally, too, than just from their perspectives. So I'm a 6th-year student in the GGE. I study plant-soil microbe interactions, nitrogen cycling, some soil ecology, mostly in agricultural systems. I know there's a lot of us, but I'd be curious to know just sort of generally, maybe we can't go around and do introductions, but maybe I could at least get a sense of how many people have used vegan before. So a lot of people. Okay, so there'll probably be folks that know at least as much as I do. And do people use it mostly for sort of, I'll say, traditional community ecology analysis, like species abundances with environmental variables, or is that mostly what you guys are using it for, or totally different stuff? Anybody have anything different that they're using it for, besides of just, okay. Well, I use it for everything from that type of traditional community analysis to gene expression data to spectroscopy data. So today, I just want to help folks to sort of develop some basic skills in vegan. So I'm not going to be going real, as you might expect, deep into the actual statistical methods, just enough to sort of understand what we're looking at. You know, I'll embarrass myself if I try to talk about these things too deeply. So just a quick overview of what we'll cover. We'll cover some different unconstrained ordination methods, just the real basics, PCA. We'll do some non-metric multidimensional scaling, talk a little bit about dissimilarity indices and how to calculate those in vegan. We'll move on to sort of dealing with two matrices at once. This is generally like how you relate community data to environmental variables that might be driving those patterns. But you can think of that more generally as just sort of how is one matrix of variables related to another. So we'll start by sort of just fitting environmental vectors over ordination. We'll look at one example of a constrained ordination technique called redundancy analysis. We'll talk briefly about partial RDA and variance partitioning, and we'll look at how to relate dissimilarities and environmental variables through permutational tests. So please stop me at any point if you have some questions, or if you're going too fast or something's not clear. And then just some resources here that you can look at after the presentation if you're interested. So yeah, we'll just kind of dive right in. So we'll talk about unconstrained ordination first, and we'll start with PCA. And the data that I'll be using is some soil biogeochemical data. So this is just some of my own data, and part of the reason I'm using it is that, as you all, I'm sure, are probably aware, PCA, one of the assumptions is that there are linear relationships among the variables, and I know that this data set more or less fulfills some of those objectives. So it's a data set that has, like I said, a lot of different soil variables, and there's one factor that we'll be looking at, and that's just the field. So there are 13 fields. There are 6 measurements per field. There are also, of course, ways to implement PCA just with some standard R functions, but the way that vegan does it, so first, obviously, we'll just load up our vegan package, and we'll run our PCA with this function called RDA right here, and we'll come back to RDA in a little bit. And so I would imagine that there's a range of sort of R experience, so I'm going to make sure I try to cover everything sort of in detail and not assume that you know what's happening. So I had one factor in that data frame, so I don't want to do my PCA including that factor. So I'm just saying select the first 15 variables here, and so I'm not using that field. The scale argument means I'm going to scale the data to a mean of 0 and a standard deviation of 1, so each variable. So basically it means I'm going to be working on a correlation matrix instead of a variance-covariance matrix. It's because these variables are all made on different measurement scales, so we don't care about the actual magnitude of the different variables. This data set doesn't have any missing values, but if you do, if you run it like this, you'll just get an error message. So there is an na.rm equals true statement that you can add if you have some missing values. That's not great in the sense that it's going to take out that entire sample of whatever missing value is there. So if you have a variable with a lot of missing values, that's going to be problematic.
And do you know, if you just have one column, for example, where there's a variable missing, but you have the other 14, there's a way to have it look at all 14 and not the one missing variable? Because I've been running into that where I have most of the data, but not.
Yeah, I mean, you could just not. I mean, are you asking if you can just not include that whole that variable?
Yeah, run that for 1 through 15, those variables 1 through 15, but have it skip on that one row, for example, that's missing.
Oh, so if you add that NA remove statement as an argument, it removes the whole row.
Right. I'm wondering if anybody knows really if there's a way to run it where it only removes that one variable and still looks at everything else.
Somebody else may know, but as far as I know, you can't. Yeah, you can't do that. And you could do something sort of, sketchy, like impute the data or something, and then see how much of a difference it makes, with or without. But yeah, that's the only way that I would know how to do it. And so this, I just wanted to throw in a plug for dplyr here real quick. This is so this is kind of an aside, but this is an awesome package to manipulate data frames. It builds on plyr. And anyway, it's just a different way of selecting what variables I'm going to use. So it's a little more intuitive, so that's what I tend to use.
And we have a recorded screencast from the beginning of the quarter of how to use dplyr for one of my
awesome.
So
that's great. Cool. Okay, so so we created our results as soil.pca, and this is just taking a look using the summary function. So you can see some of the output here. For instance, some things that you typically care about in a PCA would be the proportion of variation that each axis explains. And so you get that here with the proportion for each individual axis and then the running total down here. So for instance, these first two axes are explaining 52% of the variation in the data set. This display equals null argument here is just suppressing some of the output. Otherwise, it just gives you this giant list. It'll actually give you the loading scores and the site scores and for all of your samples. And so that's just suppressing some of that sort of verbose output there. If you wanted to look at loading scores on their own, it's not necessarily intuitive, but Vegan has a function called scores. So you give it your result, you give it what axes you want to look at. So here we just want to look at the first two axes, and then display equals species. So again, Vegan was written for community ecologists in mind, so some of the language is related to that. So that basically this means your variables as opposed to your sites, and with no scaling of those variables. And then Vegan has some built-in methods for dealing with its objects, including plotting them. And so if you just plot your result using the generic plot function, you'll get you'll see your sites with numbers, and then your species or your variables in red here. But as you might imagine, these are pretty ugly. So we can talk a little bit about how to customize these to make them prettier for publication. So the way you kind of do that is sort of building them up step by step. One thing that you want to make sure of when you're doing this is that the scaling that you're using of your sites and your variables are the same if you're going to be sort of plotting them in different plots. And so I'm setting my scaling variable just to 3 here. I think there are 0, 1, 2, and 3 are the accepted values here, and you can look in some of the vegan tutorial resources to sort of see what that means. So then I'm going to this first command just plots a blank plot with the right range of x and y values with the right scaling. And then I'm going to add text of the variables using the text function. Again, I'm displaying what the species, I'm coloring it black, and it's scaled to the same as the original plot was. So I can get my variables on one, and then a lot of times if you have a lot of variables or a lot of sites, things are going to be overlapping. It's ugly, so maybe you want to do sort of things on 2 plots. So you might do that via another set of commands. And here I'm showing how to do this while also visualizing some factors that you might have. So again, I'm going to call a plot with nothing on it. And then I'm going to display points that represent my individual sites. And so those are the dots, the open circles that you see here. Then I'm going to use one of 3 sort of neat functions that Vegan has for how to graphically display factors. And so I mentioned I had 13 fields that were in this data set. And so I'm going to use this RDA ellipse function to draw a little, call them 95% confidence ellipses around the 6 points that represent my fields. And so there's a number of possible arguments, so you can really sort of play with how that looks. And we'll go into even a little more detail with this when we get to the redundancy analysis. And we can talk about how to give different colors to these ellipses and that kind of thing. These other 2 options look like this. This is a combination of RD spider and RD hole. So RD spider is going to move from the centroid of your factor and draw little lines out for each of the individual sites or points that make them up. And then the RD hole will draw like a dotted line around the whole group. So just a couple of different ways of showing groupings on your ordination plots. Okay. And so now, if you really wanted to sort of make this publication ready, you probably want to export a PDF. And so this is basically the same code that I just showed you. I'm doing some other little tricks that I like to use, a package called Extra Font, which allows you to use some different fonts. So let's take a look at what this looks like. So now we have our PCA, we have a plot of our variables, a plot of our sites, and our groupings side by side with the same scaling. It's nice and easy to read, and you could tweak this a little more, but it's basically ready to go. Let's get back into. And then if you really wanted to customize stuff, you can extract the site and the variable scores for, I'll just say, maximum flexibility. And so you can make a data frame for your site scores, a data frame for your variable scores, and then you could pass these on to other packages like ggplot. But the downside of doing that is that these built-in functions like RDA ellipse aren't going to work, as far as I know, in those other graphing packages. So you know, it's sort of a trade-off depending on how much flexibility you want. All right, so any questions on PCA or the plotting or anything like that? So moving on, now we'll do some non-metric multidimensional scaling. The data that we're using here is built into the vegan package. This is a data frame of 44 species and 24 observations. And you can see a lot of zeros. So this is not the type of data that would be really amenable to something like PCA, obviously. Vegan has a nice function that I'll get into in the next slide, into sort of its guts a little bit, called meta MDS to run the NMDS. So here's, we're giving it our data. We're specifying a dissimilarity measure. And I'll kind of tell you what the other arguments mean on the next slide. But actually, let's just go and then take a look at that. So this meta MDS is a wrapper function. So it wraps a few different recommended procedures into just this one function. First, it's going to take your raw species abundance data and standardizes it so you're not so that the abundance isn't influencing your measure of dissimilarity. Things like Bray will abundance matters for things like Bray. So if you're not concerned about species abundance, you're just looking at composition, then you're going to want to standardize it first. So then it calculates the specified dissimilarity matrix, and then it runs the vegan function mono MDS a bunch of different times, however many times you specify, with random starts, and it does that for as many times as it needs to until it finds two similar configurations with a minimized stress value. And then it rotates the solution so that the largest variation of site score is on the first axis. And then there's some other details that you can look into in Vegan Tutor, but that's sort of the basics. So again, this try max is the number of random starts that it tries, and then the trace means false. It's not going to output each one of those starts. It'll just give us the final results. So again, we can use the default plotting function and also customize it in basically the exact same ways that we were doing with the PCA. But there's also some other built-in functions that can help out with plots. I haven't used these too much, but for instance, there's this one that if you have long Latin names, it'll shorten Latin names into like 6-character variables. There's ordi-torp, which will, if you have a lot of overlapping variables and sites, they overlap when you plot them, it'll make some decisions about whether to plot a variable name or a point, this kind of thing. I haven't used these too much, but they seem like they could be cool. I'll be like I end up doing a little bit of tweaking usually in like Adobe Illustrator or something like that afterwards, rather than trying to rely on these. So I don't know if anybody else has experience with these, but so then there are a couple of ways to evaluate your NMDS mapping. One is the stress plot function, and so this is going to map or plot the observed dissimilarity values versus their distance on the ordination. So like ideally, if that NMDS is a good representation of actual matrix of dissimilarity values, then you'll see a strong fit between these data. Another thing to look at is this this goodness of fit. So we can calculate a goodness of fit for each site with the goodness function, and then there's just some simple code here to show this graphically. And so the larger circles around these sites are representing plots that don't have as strong of a fit with the sort of originally with the original dissimilarity matrix. So just some ways to check out how your NMDS is looking. So maybe you want to compare a couple of different ordinations. So that can often be difficult because they might have slightly different orientation or scaling. And so there's a function called procrustes which allows you to make some comparisons. So for instance, if you were trying out some different dissimilarity indices for your data and you wanted to see how that affected the ordination, aside from just like kind of holding them side by side and trying to look real carefully, then you can use this function. So here I'm just doing another NMDS. This time I'm using the Euclidean distance, which not going to be a good choice for most community analysis, but it'll give us a really different ordination. And then I'm going to use the procrustes function to compare our Bray ordination and the Euclidean. And so this is what that's going to look like if we plot that result. And so it's showing the shift in sites between those two ordinations. So you can see some pretty dramatic shifts between the two. And so that'll work for any, you can compare an MDS ordination with PCA, the first two axes of a PCA. It's very flexible in what it allows you to compare. You can also look at those differences as a function of your sites. If you wanted to sort of get more detail about which sites exactly were the problem ones, the really different ones.
That'll just compare two, I assume.
Yeah, as far as I know, it just. Yeah, I don't think it can handle more than two, but that's a good question. Yeah, I don't. Yeah. So MetaMDS is automatically, like I mentioned, it's automatically standardizing your data, and then it's calculating whatever dissimilarity index that you specified. So it's sort of taking care of it all behind the scenes. Maybe you want to sort of do that, just get the dissimilarity index. Well, the function VegDist will do that for you. And so it has, I think, maybe about 10 or 12 different dissimilarity indices that it can calculate. If you just look at the help file for that function, it'll give you the list of all of the ones it does. And it outputs an object of class dist. Another plug for this book, Numerical Ecology with R. This is so this is available from Springer for free if you're on UC Davis, but IP address. So it's got a lot of good stuff on multivariate techniques, and it's all in R. A lot of it's with vegan, some of it's not, but it's a really good resource. Let me get back here. Yeah. Evidently, it lost my presentation. So, any questions on NMDS or distance or dissimilarity indices or anything like that. So now I'll talk about a couple of different ways to relate community data to environmental variables. Or again, more generally, if you have a matrix set of one variables that you want to relate to another. So I'll say the simplest way to do that is to overlay environmental vectors onto an ordination that you've already done. So let's take a look at some data that we'll use. Again, this is with the vegan package. These are chemical, I think soil chemical variables from the different sites where they did the species counts. So it's 14 variables. And let's see how they map onto the ordination. So we're going to use the function envfit. Here, we're going to give it our NMDS result, the Bray dissimilarity. And we're going to give it the environmental variables that we want to use. And this is it's going to base the significance of these fits via permutation tests. So we're specifying how many permutations we want, and then just displaying the results of that. And so the first two columns are the direction cosines of the vectors that this is giving us, and we'll look at that on the next slide. Then the R squared is the correlation coefficient between that variable and the two axes, and then a permutational significance test. So then we can plot these. Again, just with we first are just calling a plot and displaying, just for clarity here, just displaying only the sites. And then we're going to plot the result of that envfit that we just did, and then this Pmax argument here is just going to only plot the ones that are significant at 0.05 or below. And so, the way you interpret this, probably are familiar with this, but the arrow is going to be pointing in the direction of the most rapid change in the environmental variable. Basically, that's the gradient of that environmental variable. And then the length of the arrow is proportional to the correlation between the ordination and the environmental variable, or the strength of that gradient. So you can see here, aluminum and iron are going in opposite directions to manganese and I guess the depth of maybe the humic layer or something like that. Again, you've already done your ordination, and now you're just fitting some environmental variables on top of it. So envfit will also work with factors based on your factor centroids. But this does imply, or you're assuming sort of a linear relationship between your ordination and the environmental variables, which may or may not be a good assumption, depending on your data, of course. Vegan has another function called ordisurf, which fits surfaces of environmental variables based on generalized additive models. This isn't something that I've used a lot. It works maybe with one or two variables at a time. It's going to be drawing these sort of surfaces across your ordination, so too many gets really complex. But you definitely have some nonlinear relationships in a handful of variables. It might be a good way to look at that. So now we're going to talk about a constrained ordination technique. And so now, instead of just overlaying environmental variables onto an ordination, we're actually using environmental variables to constrain the ordination. This basically is going to be only looking at the variation in our response variables, maybe our species matrix, that can be explained by our explanatory or environmental variables. So basically, this is combining multivariate regression, where you have multiple x's and multiple y's, and principal components analysis. So it's related to PCA. It's based on Euclidean distances. So for community composition data as response variables, there's some alternatives that are based on this. One is a so-called distance-based RDA, where you're starting with not a raw species abundance matrix, but a matrix of dissimilarities. There's a nice explanation of that in numerical ecology with R. Another option is a transformation-based RDA, where instead of you're transforming your species abundances and then doing a regular RDA, so it's slightly different than the distance-based RDA. And then there we go. And then of course there's classical options like either constrained or canonical correspondence analysis. They're the same thing. That are going to be based on a chi-squared distance. So that's, you get a modal response. It can be good for some data. Okay. So now I'm going to be going back to the soil data that we looked at in the PCA. So we had that data was sort of soil biogeochemical variables. Now we're going to be looking at some soil enzyme activities. So you can think of this is basically our Y variables, and we're going to use the soil properties that we looked at in the PCA to ask basically how do soil properties drive soil enzyme activities. So you might be asking a question, really generally, how does this set of environmental variables drive the community composition that I'm seeing across a range of sites or conditions. Okay, so I'll show you a procedure here to sort of whittle down the explanatory variables that you might be using, with the sort of caveat from the get-go that selection procedures should always be used with a lot of caution. But that there are some nice functions in vegan for doing this. I'll show you how to do it. There's a nice paper on the implementation of this particular technique. So basically, I think it was 15 soil variables. Maybe I want to try to whittle that down to as few as possible, that without sacrificing any explanatory power. So first, I'm going to run a redundancy analysis with the full set of environmental variables that I have. And so my response variable, again, is that matrix of enzyme activities, the E and Z. And then we have a typical sort of model, as explained by tilde here. And then this dot is just a shortcut to say include all of the columns in the data frame that you give it. So our data is going to be the same soil variables that we did the PCA on. We're going to include all of those columns, and we're going to scale or standardize the soil variables. Now we're going to, so you have to run, you need this result here. Now we're going to run this forward selection algorithm with this function called RD2 step, R2 step. First, we're going to give it sort of a null model to start from, and so this is an RDA just with an intercept. And let me point out one thing here. So RDA was the same function we used for PCA. The only difference was we weren't giving it a second, we weren't giving it a model statement, right? So it's just sort of building up with additional data frames. So again, in our forward selection procedure here, we're starting with sort of a null model, and then this scope option here is going to basically say, take all of the variables that were included in this first RDA here as the most complex model possible. So this is just sort of a shortcut for specifying that, as opposed to writing out each individual variable in the model statement. So So it's going to be a forward selection procedure. And so then we run it, and we can take a look at the result of the final variables that it included with the ANOVA function. I'm not going to pay too much attention to the actual output of the ANOVA function. Really, I'm just focused on what's left included in the model. So this I think it ended up with 11 or 12 of the original 15. So most of them still made it in. So now we'll take these variables and run the actual redundancy analysis that we're interested in. So now I just am putting in the variables that were left after that forward selection procedure and fitting this model. And then we'll take a look at some of the results of that. So first off, we can ask the question, just how much variation do the soil properties, how much variation in the enzyme activities are these soil properties explaining, adjusted for the number of parameters, adjusted for the number of explanatory variables that you're using. So it's about 65%. And we can see in just the summary function, some other, that's not too small. So it's giving us something similar here, the proportion of constrained variation explained, but this is not adjusted for the number of explanatory variables, so you don't want to pay any attention to that. Now, and then down here, this is giving us for each RDA component the proportion of the constrained variation that's explained. So, for instance, the first two axes explain 56% of the constrained variation. So that's, I won't go into any more, it's getting into any more detail there, but those are some of the key things that you want to look at from the output. Other things to look at, there's a function called the variance inflation factor. You'll notice that we're using .cca. I don't know why it's implemented like that, but instead of RDA, it's using CCA for this purposes. This is a good time to say that all of the ways that we're doing this redundancy analysis would basically be identical for canonical correspondence analysis, which is the CCA function. So if that's something you're interested in using, it's going to be really similar to running an RDA. But what this is telling us is it's basically showing us whether we have redundant information in some of our explanatory variables. The heuristic that I've heard is that value over 10 means that there could be some issues with redundancy, and so this is something I would want to follow up on later. You could imagine that soil nitrogen and carbon are going to be highly correlated with one another, so they have big variance inflation factors. You can look at permutation. If you want a significance values for sort of the whole RDA, how well are these soil properties explaining the soil enzyme activities? You can do a permutational ANOVA. As you might expect, it's doing pretty well. We have a lot of explanatory variables. But you can use this ANOVA.cca function. It has some different arguments you can use. For instance, you can choose by axis and then get a significance test of the different RDA axes. You can look at individual variables. So if you look at the help file for this one, it'll kind of give you all of the different statements you can use there. So so now we'll do some plotting of these results. because now you've added the ordination plots for these get really cumbersome because now you have, your response variables, your explanatory variables, your sites, things get crowded. So I think paying attention to how you plot these is really important for, actually being able to interpret them. So we'll take a look at the PDF in just a second, but first, actually, we'll just go ahead and open that up, and then we can bounce back and forth a little bit. Okay, so again, so now we've plotted our response variables in black, and our explanatory variables in blue with arrows. So let's take a look at how we do that. So just like we were doing with the PCA, we can first set up just a blank plot with the type equals n. Then we can add our response variables with display equals species, give them whatever color we want, again making sure that the scaling is specified in the same. Then we can add the explanatory variables with display equals BP, and output a PDF that you may still need to tweak a little bit, but is definitely more readable than having sites on here as well. Okay, so how to deal with the sites. I mentioned we had 13 fields, but there were also 3 types of management across those fields. And so now we want to let's try to give those ellipses that we made earlier with the PCA. We'll try to give those a color based on this second factor, which is management. Let me just show you what that looks like first, and then we'll go into some of the guts of how to do it. It's not overly straightforward. So this is what it's going to end up looking like. And again, side by side, this plot and that plot make a nice sort of, relatively clean way to look at the results of the ordination. So with that in mind, let's take a look at how we do it. Maybe somebody else has figured out a better way, but as far as I know, this is well, it's the only way that I figured out how to do it. So first, we're going to create a new data frame with a code for just our 13 fields, 1 through 13. And then a vector that specifies a color for each of those 13 fields. We're going to open up our new PDF. We're going to, again, do just a blank plot. And then we're going to have to do a loop where we call RDA ellipse 13 different times. And so we've got a loop. We're going to run it from 1 through 13. We're working with RDA ellipse, pretty much similar to how we did before, with a couple of key differences. This is specifying, this isn't a difference, but this is specifying the factors, the factor grouping right here. One of the key differences is going to be in the show.groups argument. So we're only going to show one, it's only going to draw one ellipse at every iteration of this loop. So in the first cycle, I is going to be equal to 1. So it's going to call back to this groups data frame, and it's going to only code the field number 1 because it's going to be looking for row 1, column 1. And the color of that is going to be specified by, again, our groups data frame, and it's going to look for color in row 1, column 2. And so I hope that makes sense. And then on the second time around, it's going to be, I is going to be equal to 2. We're going to plot the field 2 with the color specified in row 2. And it's going to work through that 13 times to give us the plot that we looked at. So not that straightforward, but it works. It works pretty well. Any questions on how to do that? Any suggestions on how to do it better? I don't know. So one other analysis that you might be interested in doing is looking at a partial RDA and also variance partitioning. So let's think about what happens if we want to add a third matrix into the mix here. So maybe this is the spatial location of all of your sampling sites. And maybe you want to try to account for spatial autocorrelation in this analysis. Then you could do what's called a partial RDA, where you condition your analysis based on this third matrix of variables to remove their influence. And that is not a statistical way of saying it. That's how I understand it. I'm not going to delve into this real deeply. It's pretty easy to specify. You just add another. Basically, you're just adding another matrix onto the into the RDA function in one of two ways. Either listing out your sorry, that should be Y right there. Your response, your explanatory, and then your conditioning variables. Something else you might be interested in doing is sort of related to this partial RDA, but now maybe you're actually interested in the contribution of that third matrix to the variation in your response variables. And so you can you can partition the variation in your response variables into that is explained by matrix of variables Y, a third matrix of variables Z, and then shared correlation or shared variance between those two. So the unique contribution of sorry, I keep saying Y, but the unique contribution of X, the unique contribution of Z, and their shared contribution to your response variables Y. You can do this pretty easily with the function var part in R. It's going to run 3 different RDAs of Y by X, Y by Z, and then Y by X and Z together with, and then compute an adjusted R squared of each set, and then just sort of use some algebra to figure out what the sort of unique contribution of each explanatory matrix is. So that can be pretty useful. And then finally, I just wanted to really briefly talk about how to do some multivariate analysis of variance based on dissimilarities. So what we were looking at before is, at least with the constrained ordination, was just the ordination based on those environmental variables. But sometimes we might want to look at those relationships, the species-environment relationships, without any ordination or in the whole space. And so the Adonis function is one way to do that. again, just taking some data built into the vegan package. We have the Dune, which is species abundances. There's about 24 variables, and then some environmental variables, including some factors. And so with the Adonis function, we're going to say, okay, here's our response data set, set of species abundances. We're going to calculate a dissimilarity array matrix. And then we're going to ask how this is a factor management, and then a continuous variable, the depth of the A1 soil horizon as explanatory variables. And we can look at the output. This is based on permutation tests. And so we can look at the output, really focusing just on the R squared and the p-value. So management is highly significant, and it's explaining about 35% of variation in that Dune data set. A1 is less significant and explains less variation, and the interaction is not significant. So again, that's just a really, really brief introduction, but that can also be a really useful function. So yeah, I thought it might be, rather than going into too much detail, maybe we can talk about some questions or data people have or whatever. So I hope that was useful.
Well, early on, you mentioned that some of these had to be, like the ordination had to be linear. Are there any of these? I mean, the NDMS is non-parametric.
Yeah.
What about if you don't have, you don't have linear relationships between the variables?
So you have a couple of options. You can use something like an MDS, which is going to be based on a dissimilarity matrix as opposed to your raw data. There's another technique, and somebody else, please chime in if you know more about this than I do, but called principal coordinates analysis, which is basically PCA, but you're starting with a dissimilarity matrix as opposed to the raw data. Now, I mean, there's also you'll notice, if it's just a couple of variables, so for instance here, I have most of my variables, I'm pretty, have linear relationships among them, but these two, soil ammonium and nitrate, have a long tail, and so a simple log transformation makes those behave a lot better. And then, so you can do some transformation beforehand if you have just a couple of variables maybe that are problematic. But yeah, there is you can do the principal coordinates analysis, and it's just basically doing that, calculating that similarity matrix for your data using that VegDist function, and then I think you just can use the RDA function on that. Maybe wrong. Somebody else knows. Please chime in.
We'll be posting the video, the slides, the code associated with the slides.
Yeah.
Tim's personal phone number on the Hero blog, and you can just go to the Hero homepage, and it'll be in our tutorials and such. And I don't know. Yeah, I guess people online can hear me. If there's anyone online with questions, you can type them into a little box, and they'll come up too.
And you'll tell me what they are.
Yeah, and that'll work when we end this. That should still be up.
Okay.
I think we thought also if people are working on some of these things now, we have a lot of new faces here this week. We have this 2 hour blocked off, and we usually have these presentations for the first hour, and the second and the second people work on whatever they're working on to get help, be it on vegan or something else in our, that's what we're here for. Especially while we have Tim, if you're working on something and you get some ordination plotted, he can help you out while we're here.
Yeah, definitely. Mm-hmm.
And maybe this is related to the, I don't know how to pronounce it,
The Procrustes thing? That's how I pronounce it. I don't know.
So I guess this starts that I've heard the critique of the NDS that it's related on rank abundances, so that you're actually losing a lot of variation. And I guess, can you use that function, the crusty one, in order to see what types of variation you're losing in using rank abundances if you're comparing that, your non-metric dimensional scaling to your PCA? And is that what that function could be used for? Or am I misunderstanding?
No, I think you could definitely use it to look at, just from a visual perspective, how, how your ordinations are changing. Is it compressing different parts of your gradient, or, giving it some sort of weird oblong, elongating other parts of the gradient. Yeah, in terms of a more quantitative way of looking at it, I don't know if Procrustes does that or not. Does anybody else know? I'm not. I don't know if that helps at all.
No, I think it's sort of, I get confused about it being two different. You're using RDA or you're using non-dimensional. I don't know how to compare them.
Mm-hmm.
Which one?
Yeah, I mean, if you I guess the NMDS is going to be sort of showing everything on two axes, right? Well, unless you tell it to do more. And I would guess if you were comparing that to maybe like a principal coordinates analysis or something, which might be a better comparison because it's also, you could, base that on a similar dissimilarity matrix, and then look at how that, and then just look at the first two axes of that principal coordinates analysis and see how it's changing the separation on your sites, your factors, or whatever it is you're looking at.
Have you had an experience with Adonis whereby the significant values of such change with the permutations that you
Yeah, and I guess that's related to, this is really the limit of what I know very well, but if you, let's say you only give it 100 permutations, can only give you a maximum p-value of like 0.01. If you give it 1,000, it can give you a maximum p-value of 0.001. So now it won't just increase arbitrarily, but it can. Is it changing like in a random sort of way?
No, it seems that it's
So give it like 100,000, and then there should be a limit. Yeah. And one other interesting thing about Adonis that I haven't played with too much is I wanted to try to use it for some data I was using, looking at in another way with a mixed model. And there's an argument called strata that you can use, which basically will only run, it specifies whatever one nesting variable. So it has to be a really simple structure. But let's say you had 4 sites, and you wanted to treat site as a random factor. Then you could specify in the Adonis statement strata equals site, and it only runs the permutations within each site individually. And then I don't exactly know how it gives you just one answer, but from what I understand, I've just been looking into this. From what I understand, it's sort of a way of dealing with some nestedness issues. in data. I don't think it can get very complex, though. But maybe people are working on that. I don't know.
All right. Thanks, Tim.
All right. Thank you.